So we started off, first of all, by talking about many electron systems. Now, this is important because many electron systems are what we actually have to deal with. That's the physical reality of modeling with electronic structure. So I'm an electronic structure theorist. I do a fair amount of practical calculations, mainly on semiconductor nanostructures, but I also develop a DFT code. The DFT code I developed is called Conquest. It's a linear scaling code. And we were the first the first code to show that it was possible to do millions of atoms of DFT. So we've done over 2 million atoms of DFT, and we've scaled to over 200,000 cores. So that's my kind of background. But so this is why it's important to understand many electron problems, or at least to have some idea of what goes on with many electron problems. They underlie all of electronic structure. And these 2 weeks are going to be sort of giving you the background data to how we go from the insoluble many electron problem to DFT, and to some extent other approaches such as Hartree-Fock. So what do we talk about under many electrons? We talked about the Pauli exclusion principle, and in particular we were thinking about indistinguishability. So how you've got electrons which can't be distinguished from each other, and therefore when you take into account the wave functions, you have to allow for exchange between particles, and when you exchange particles you introduce a minus sign because electrons are fermions. And so this introduces very, very complex wave functions. Okay, so the basic wave functions, which in a many body system of electrons or fermions in general, will be very complex, and they are factorially complex as you increase the number of electrons. That's one of the reasons why we can't solve for more than 2 electrons exactly. We did look briefly at the operators for kinetic and electronic and potential energy, but they're not really very different to anything you've seen before, so I'm not going to go over those. And then there were a few little bits of background in the notes which talk about the standard quantum mechanics approaches of expectation values and orthogonality and the variation principle. Again, I don't think I'm going to go over that. If you've not done any quantum mechanics, if that's not your background, then I can't cover it in this lecture. If you have done it, you should understand that. So I'm going to propose to move on in just a second to the Hartree-Fock approximation. Anybody got any questions so far? No? Okay, all right, that's fine. Do feel free to unmute and shout at me as and when. So let's just briefly touch on Hartree-Fock. So Hartree-Fock is a very, very basic approach to electronic structure, to many body interactions. It's probably the first practical method that was developed for solving for electronic structure. And it has a number of key ingredients. So we have a wave function, capital psi, which is a Slater determinant. And that's the simplest many-body wave function that you can have that obeys all of the appropriate symmetrizations. The details of that are given in the notes. And we then introduce the Hamiltonian, and we note that the Hamiltonian is made up of 2 kinds of things. One is single electron operators, and the other one is 2 electron operators. So we have the kinetic energy, which is single electron, and the electron ion potential energy, that's also a single electron operator. And then we have the electron-electron operator, which is 2 electrons. So we're going to say this is 1 electron and this is 2 electrons. Okay, so they're distinguished because they take different forms, and it's the 2 electron terms which are more complicated. So the kinetic energy is actually very simple. So it ends up as just being you write it as the kinetic energy, the sum of the kinetic energy of the individual single electron wave functions. So let me just clarify that actually for the Slater determinant, it's made up of single electron wave functions. Which we're going to write as psi, little psi subscript I. And so the kinetic energy, you can show that the the expectation value, sorry, I'm just going to rewrite this. The expectation value of the kinetic energy, which you would write as the many-body wave function acting on the kinetic energy operator, many-body wave function, again, just integrated, that can actually be shown to be the sum over the individual single particle wave functions of the individual single particle kinetic energies, which is minus a half del squared psi I. Please note that frequently when we're doing electron structural quantum mechanics, we work in what are called atomic units. In atomic units, h bar is equal to the mass of the electron is equal to 1 over 4 pi epsilon naught is equal to 1. Okay, which is why the kinetic energy operator that I've put in there has a minus a half rather than the minus h bar squared over 2m that you might expect to see from sort of standard quantum mechanics. So that's just reminding you there. And in atomic units, we have units of energy which are called Hartrees, and we have units of distance which are called Bohr radii. For the electron-ion interaction, we have a very similar result. So the electron-ion interaction, the expectation value, which gives us the energy. Again, we can find that that's just the sum over the single particle electron-ion interactions. I'm just going to write that as a VRR on the side like that. So what we found is that the Hartree-Fock approximation, and I haven't derived this, but I'm just quoting these results. For the single electron terms, we're just finding that the total energy is given by the total energy of the individual single electron wave functions, which makes life much, much simpler. It means that we don't have to worry about that complex many-body wave function. Of course, we do actually have to worry about that, and that comes in when we think about the electron-electron interactions. And so we find that the electron-electron expectation value, which you might write in terms of the many-body wave function, so this capital psi is the many-body wave function, and that's going to be given by capital psi, and then the form of the operator is very simple, saying it's I not equal to j, it's just a classical electrostatic term. You've got 1 over the distance between the two electrons. Got capital psi again. Okay, so again, notice that we're working in atomic units, and so the 1 over 4 pi epsilon naught you would expect to see for an electrostatic energy is to become 1, as has the charge on the electron. And so we just have this very, very simple form for the electrostatic interaction between the electrons. Now, this is where it becomes interesting, because what we find is that if you simplify and go through some maths, which I'm not going to do, but you end up by finding that there are 2 contributions to the electron-electron interaction. So the first is the classical electrostatic energy. As you might expect, and you can write that in terms of a charge density, as you would classically. So that's just a simple solution. But you also have a second term, which is known as the exchange energy, which is entirely quantum mechanical and is the cause of a large amount of background theoretical work, computational effort, and computational implementations. And so let me just show you what the form of those 2 are. So we tend to write these as EH and EX. And so the Hartree energy, or the electrostatic energy, is just a half times the sum over I and j of, and you have a double integral over places in space, dr prime, and then you just have psi I of r squared, which is a charge density, psi j of r prime squared divided by r minus r prime. Okay, so that's an absolutely standard classical electrostatic term, but notice that it's made up of the interaction between 2 of these single particle wave functions, the psi I and the psi j. When we write the exchange energy, it becomes more complex, and I'll write it like this. So there's a minus sign there, so it always lowers the energy. Again, we've got the sum over I and j and a double integral over 2 positions, dr and dr prime. And then what we have is the following. We have psi I star of r, psi j of r, and then you have psi I of r prime and psi j star of r prime divided by r minus r prime. Now, what's the difference between this EX and this previous EH? Well, the difference is that with the EH, you could combine the psi I star and the psi I into a single charge density, but here you can't do that because psi I star is at point R and psi I itself is at R prime, and it's the same for psi j. So this is the quantum mechanical exchange operator. It encapsulates the many-body approximation that's actually present within Hartree-Fock theory, and it's responsible for most of the processing that you have to do when you're doing this kind of calculation. Hartree-Fock itself is actually not very accurate. It's really not used for very much except as the basis for other more accurate calculations. So it's often used as the input to something else, but it's a good way of getting an insight into what goes on. That's about all I want to say about Hartree-Fock. So the key things to take away from this are that we start with this Slater determinant, which is a complex many-body wave function, which is made up of single particle wave functions. We then write down the Hamiltonian. We break it down into these two contributions. We've got the single particle and the two particle. I didn't do the maths, but you can show quite easily that the single particle terms are equivalent to the single particle wave functions on their own, so you don't have to worry about the many-body terms there. The two-body interaction, the two particle, which is the electron-electron, has two contributions, one of which is a classical, one of which is quantum mechanical. And the quantum mechanical part, the exchange energy, is really, that's the only complex thing, the only difficult thing to calculate in Hartree-Fock theory. That's a very brief overview, maybe of the first half of the material. Does anybody have any questions at this point? No? Feel free to put it in chat if you don't want to speak. Okay. So, I mean, if you don't ask me questions, I can't answer any problems, and I don't know where misunderstandings are, but that's fine. If it's all okay for now, then we'll just move on. Okay. All right. So we'll move on to the second part, which is where we start dealing with a concept. So the concept is the uniform electron gas. So this is a useful thing to think about, first of all, because physicists like to think about abstractions, and the uniform electron gas is a wonderful abstraction. It's a way of thinking about many-body interactions and all these kinds of difficulties, but in a way that we can generally get a handle on. It also is important in retrospect, i.e. looking back, because many of the ideas that you encounter when you think about the uniform electron gas actually underlie density functional theory, which is the thing that an awful lot of electronic structure people use and calculate. So it gives you a good kind of insight into the origins of DFT and into the basic ideas that underlie it. So let's just take a step back and look at the difference between the uniform electron gas and Hartree-Fock. So Hartree-Fock theory, we're postulating a set of single particle wave functions, which we then have to mix together to make a many-body wave function. And so that we're doing complex interactions, and everything is to do with the quantum mechanics and the wave functions. The uniform electron gas, by contrast, deals only with charge densities. Okay, so that's all we're thinking about. We can include quantum mechanics and many-body effects, but we tend to work primarily in terms of charge densities. And this is what DFT also relies upon, is it works mainly with the charge density, and that's what simplifies and makes it worth doing. Okay, so that's the kind of the key concept that you need to take away from this, is that charge densities make things easier. So we'll start in one dimension. So in 1D, which is making things as simple as it possibly can be, is we're going to assume that we're going to have a box, a one-dimensional box, which I'll draw. I know this looks like it's two-dimensional, but it's just in 1D. and we'll put the origin at the middle, and we'll say it goes from L over 2 to minus L over 2, but we'll make it periodic. Okay, so that means that we're going to repeat this infinitely in space. And so you can show that the wave functions that solve this, I mean, this is just the same as first year waves, is 1 over root L, and then you've got an e to the 2 pi I nx over L, where n is an integer. Okay, so these are just the standard kind of standing waves that you would, or traveling waves that you would find in any kind of solution. So these are free particles. They have a wave vector, which is kn, which is given by 2 pi n over L. And of course, the momentum is just h bar times k. And so you have an equally spaced set of wave functions, wave vectors. Okay, and when we're talking about electronic structure, if you're a physicist, you tend to think about solid state and materials and crystals, which are periodic, and therefore worrying about wave vectors becomes extremely important. In the limit that L becomes large, that tends to imply, particularly also if we allow a large number of electrons, Ne, to be large, we can then kind of write down an awful lot of the properties of the system in terms of the wave vectors and the charge densities. So because we've got no potential, there's nothing that's causing the electrons to move except for themselves. They're not interacting at the moment. So we can say that the energy of any given wave function is just h bar squared k squared over 2m, which in atomic units would just be k squared over 2. Okay, and I'm going to dip backwards and forwards between atomic units and normal units. I'll probably actually, for this part of what we're talking about, I'll keep in the h bar squares and the m's just to keep things a little bit clearer. Now, we know that the way that quantum mechanics works is that you start with the lowest energy and you fill up the different energy states, okay, until you reach the number of particles you want. And so there will be a maximum energy. That's just the energy for the electron with the highest energy. And we know that that'll be h bar squared, and we'll call this kf squared over 2m, where kf is the Fermi vector, the Fermi wave vector. And this is called the Fermi energy. We'll call epsilon f Fermi energy. Now you can derive a relationship between the Fermi energy and the charge density. That's in the notes, so I'm not going to go through it. I'll just quote it here. We say that EF is h bar squared pi squared rho squared over 8m, and rho is the density. Okay. Now, it's worth just stopping and thinking for a moment about dimensionality, so units and dimensions of problems. So we know that an energy has dimensions of, well, whatever h bar squared over 2m is, and then you multiply that by 1 over length squared, because that's what k squared is. So in this case, rho is the density, and the density is the number of electrons divided by the length, because this is still in 1D. So in this system, in one dimension, we find that the Fermi energy is proportional to the square of the charge density. That's going to change with the dimensionality of the system. So when we go to 3D, that will change, and we'll find that we end up with rho to the 2/3, because we want dimension for the energy to be correct. It's just worth kind of keeping an eye on that, thinking about dimensionality and making sure that we know what we're doing. Now, again, I'm not going to go through it, but we can show that the total energy can be written as L over pi, h bar squared over 3m, and then you've got the Fermi wave vector cubed. And again, let's just think about this dimensionally. K cubed has dimensions of 1 over L cubed, but we've multiplied by a length at the front, so we've got the right dimensions for the energy. And we can write the Fermi wave vector in terms of the charge density as well, so that's not a problem. And you do that just by going back to the epsilon f there, and you find that the Fermi wave vector is proportional to the density. Kf in this case is equal to pi rho over 2. So the total energy is proportional to the cube of the charge density that we have to multiply by the system size. And you can, if you want to, do an energy per electron. So let's say epsilon total, and that's equal to E total divided by the number of electrons. And the reason we're doing that is because if you do that, then you find that the L divided by N gives you an extra factor of the wave of the density. And so you can show that this is equal to h bar squared kf squared over 6m, which is just a third of the Fermi energy, epsilon f. And the reason that I'm sort of throwing all of these things around is because it's just important to see how the energy depends on the density, because this is something that we'll keep going back to in DFT. Okay, so DFT relies an awful lot on that kind of thing. Are there any questions at this point? Everybody happy with the idea of a uniform electron gas? The basic kind of ideas I've been throwing around? Yeah, okay, I've got one thumbs up. That's excellent. I've got somebody actually responding to my questions. Thank you very much. What is the difference between NE and N? The only difference between NE and N is my failure to put an E on the N. I'm sorry. You're absolutely right. I should have put an NE on there. Sorry about that. Any other questions before I move next? No? Okay, yes, Huan Yu, is that right? Please feel free to speak or to type in chat as you wish. I can't hear anything. Is that just me or is anybody else not? Anyone hearing Huan Yu? Not obviously. No, I can't hear him. Huan Yu, I can't hear you, so please feel free to type the question in chat if you have one, if that's okay. Okay, that's great, thank you. I'll just wait for that question to come before moving on. Question with the n in the wave vector. Yes, okay. Yep, so Kn is 2 pi n over L. And so that n can be positive or negative, and the positive and negative correspond to right moving and left moving waves. Yes, yes. So the chat says it seems to define the wavelength of the eigenfunction. Yes, so the wave vector is so k is 2 pi over lambda. That's sort of the standard in all waves, in all wave theories, whether quantum mechanical or classical. Okay, so Bader is asking what the application of this equation is. So sorry, Bader, can you be clear about what you mean by this equation? Which equation in particular? Okay, so I just had two questions pop up. So Juan Yu said, how is it related to the real system? How is the, and I presume you mean by related to the real system, you mean K. So a one-dimensional system, you can make one-dimensional systems experimentally now, and people are starting to do some very interesting questions on them. At the moment, this is quite conceptual, but I mean, it's very similar to if you think about a guitar string or a violin string, which is fixed at both ends. And if you pluck the middle, then you get a wave, which is, it's just a half wavelength fixed into that space between the two. And then if you can excite a wave which is, is a full wavelength, and you'd have to do that by plucking maybe about a third of the way along. So it's related. So the periodicity of the system has length L. So all waves have to fit into the system with length L. And it's just absolutely standard wave mechanics where you're fitting wavelengths into the system of a particular length. So yes, it is defining a periodicity. I hope that answers Juan Yu's question. Bada has said the last equation. So when we say the last equation, do you mean the epsilon top, so the energy per electron? If that's the right equation to be talking about, the one at the bottom of the screen here, that's useful, or it will be useful when we come further along, because what we'll be finding is that we can write the energy per electron in terms of particular interactions. So at the moment, it's a very simple system. There's no electron-electron interaction. There are no ions giving us a background charge. So the only thing we have there is the kinetic energy. But what we're going to see is that you can write the energy of the system, or particular energies like the kinetic energy, or in some cases the exchange energy, as a function of the charge density. And that's how DFT is built. So that's what so at the moment it's not really much of an application because it's a 1D system with no interactions. So it doesn't tell us very much about anything, but it's introducing you to the idea that you can actually write more complex interactions as functions of charge density. Does that help? Yeah, okay, I think I can see you half nodding there. So I'm going to assume that's all good. Good, okay, all right, thank you. Those are both very good questions. Everyone happy to move on, or are there anything else anyone wants to do? Juan Yu, if you could put your hand down, that'll make me less confused, unless you have another question, in which case, please feel free to type it into chat. Okay, so please keep the questions coming in chat, and we'll now move on to 3D. So we've got a 3D electron gas. And this, again, it's a somewhat abstract idea. It's very similar in some ways to the ideas of statistical mechanics that people do with classical gases. But of course, we have to account for the quantum mechanical interactions. So what changes when we go to 3D? Well, now our wave function is a function of the position vector r. And we have the normalization is L to the 3/2. So I'm assuming it's now a box, a cubic box with a side length of L, and we have an e to the I k dot r, where k is going to be a wave vector and we know that the momentum p is equal to h bar times the wave vector k. We're going to have, again, n electrons. Let me make that ne electrons, just to be clear. And so we'll have a charge density rho is equal to ne over L cubed. Okay, so again, notice that we're changing the dimensionality of the system. And we can write down almost by inspection that the wave functions k are going to be given by 2 pi over L, and then we're going to have a vector of n1, n2, n3, where these are all just integers. So this is a 3D equivalent of the wave vectors we had before, okay? So now when we think about a state, again, we're not going to interaction, so we're going to say that the energy of a state with wave vector k is again just going to be h bar squared k squared over 2m. And we'll also have, as before, a Fermi vector epsilon f which is given in terms of h bar squared kf squared over 2m, where kf is just the largest, the wave vector of the highest occupied state. We can work out what kf is just by saying that the number of electrons must be given by, and this is given in the notes, we can think about the spacing. We can say that the number of electrons is given by the Fermi vector cubed multiplied by L cubed over 3 pi squared, which tells us that the Fermi vector, the Fermi wave vector, is 3 pi squared rho to the 1/3. Okay, again, thinking about dimensionality, we could guess that that was going to happen because rho has a dimensionality of density, so it's 1 over length cubed. Therefore, the wave vector kf must have a dimensionality of rho to the 1/3. And that then gives us also the Fermi vector, the Fermi energy. So epsilon f you can write in terms of the density as h bar squared 3 pi squared rho to the 2/3 over 2m. Okay, and so notice that the energy is related to rho to the 2/3 now, and again that makes sense because we could write h bar squared k squared over 2m. K has dimensions of 1 over L, so this little term in the brackets has to have dimensions 1 over L squared. Rho to the 2/3 has that size. So we could have predicted that sort of general kind of form if we'd wanted to. If we integrate over all of the different states, you can write the total energy. So you can show, and again, this is in the notes, so I'm not going to go through it. The total energy is just given by L cubed h bar squared kf to the 5th divided by 10 pi squared m. And that's okay because L cubed multiplied by kf to the 5th, again, still has dimensions 1 over length squared. And if you want to work out the energy per electron, epsilon, that's just, again, E total over n. And you can show that that's equal to, where have I gone? I've lost my way. H bar squared over 10 pi squared m, and you've got kf to the 5th over rho, okay, because 1 over rho is L cubed over m. And knowing that rho itself is equal to kf cubed over 3 pi squared, you can then rewrite that once more and show that you've got a total of 3 over 10 times h bar squared kf squared over m. Might actually be simpler to change that and to write that as 3 over 5 h bar squared kf squared over 2m. Okay, because we're used to h bar squared k squared over 2m as being kinetic energy. That shows us that gives us that relationship, which is 3/5 of the Fermi energy. This kind of thing is quite useful to note when we move on to DFT and to what's called Thomas-Fermi theory. The other thing to do is just to write that total energy, that epsilon, in terms of the charge density. And there you find you've got 3h bar squared over 10m into 3 pi squared rho to the 2/3. Okay, and in there's a branch of, it's a fairly crude branch, there's a branch of physics called Thomas-Fermi theory, where you do work just in terms of the charge density only, and this kind of thing comes up there. So that's just taking the 1D case and generalizing it to 3D, and the main thing that we've seen is that there's just a change in the dimensionality of the problem, and therefore there's a change in many of the formulae just to reflect that. So any questions on what I've done there? No? Okay. So the last thing that we can do today is to think about interactions. In the UEG, which is the uniform electron gas. People also sometimes call this the HEG, which is the homogeneous electron gas. You'll see both of those used So what we're doing, and actually, sorry, while we're talking about different names for things, people also call this jellium, which is meant to sound a bit like a chemical element, which is like a jelly, so a sort of completely uniform situation. So you'll see uniform electron gas, homogeneous electron gas, and jellium all used in different ways. So what we're doing here is we're allowing the electrons to interact. Okay, so before now, when we've been talking about the electron gas, the electrons have not been interacting. What we're doing now is we're introducing the electrostatic interactions between the electrons. So that's again going to be the 1 over r minus r prime. And this makes the problem more complicated. Okay, so because we're having to think about interactions between electrons, we do have to come back just briefly to single particle states. And what you can show is that, as before, the individual single particle states that you need are psi I of r, or let's just say psi of r, is given by 1 over L to the 3/2 e to the I k dot r for some value of k. Okay, so introducing the interactions does not change the fundamental single particle states that we're going to use. But what we're going to add is we're going to add a new interaction operator u, which is just the standard 1/2 times the sum over I not equal to j of e squared over 4 pi epsilon naught ri minus rj. Okay, so that's the interaction between the electrons. The simplest way to solve this is to make an approximation. You have to approximate to do this. And in this case, the approximation that we're going to use is the Hartree-Fock approximation. So what we're going to do is we're going to write the many-body wave function just as a Slater determinant of the single particle wave functions, and we're going to assume that we can just solve for the total energy as I mentioned before. And so in this case, we're going to say that the total energy E is going to be the many-body wave function, the kinetic energy plus this U operator I've had above, and then the many-body wave function again. And this actually, the minimum energy for this is obtained when we use these single particle wave functions that I've got above. Now, the detailed maths, or some of the detailed maths, is in the notes. So I'm not going to go through it. There are two things that we just need to note. So first of all, the Hartree energy, that's the classical electrostatic energy between the two electrons. That cancels. And the reason that cancels is because in order to not have an infinite energy, we have to introduce compensating background charge. Okay, so before we were dealing only with non-interacting electrons, so we had no electrostatic energy, so we didn't have to worry. Once you introduce an electrostatic energy in a periodic system, if you've got a net charge on a periodic system, that gives you an infinite energy. Okay, so we have to introduce a cancelling. We have to introduce a positive background charge, and that takes away the Hartree energy. If you have a solid, okay, when you're doing periodic DFT calculations, you will always have a charge neutral system. Okay, if you have a periodic system with an extra charge, the energy goes infinite, and that's not feasible. So typically what happens is that just gets set to 0. The total charge of the system gets set to 0. So for now, we're going to ignore the Hartree energy. So of course, the other energy that we worry about is the exchange energy. And rather than go through the maths, which sort of takes a little while, what I'm going to do is I'm just going to quote the final result, which is that the exchange energy per electron is as follows. You've got EXC, or EX, is minus E squared over 4 pi epsilon naught, and then you've got 3/4, and you've got 3 rho over pi to the 1/3. remember that the kinetic energy per electron, which we were writing just as a total energy before, because that's all it was, is given by 3/10 h bar squared over m, and then you've got 3 pi rho, so 3 pi squared rho to the 2/3. Okay, so those are the two contributions to the energy of the system, and those are both energies per electron. The really interesting thing here is the relationship between the energy and the power of the charge density. So the exchange energy is proportional to the third root of the charge density, whereas the kinetic energy is proportional to the 2/3 root of the charge density. So what that means is that as the charge density gets larger, the exchange energy becomes less important. Okay, so you go to high electron densities, and actually the quantum mechanical nature becomes much less important. Now, the reason that we've derived all of this is because we will use some of these results when we're talking about DFT, but it's also to demonstrate that you can, for a uniform gas, derive an energy in terms of the gas, in terms of the charge density of the uniform electron gas. And that idea is at the very, very heart of DFT. Okay, so DFT, which we'll come to next week, starts from these ideas of the uniform electron gas and builds on them. Okay, so what we've done is I've given you, it's been very, very rapid, and I'm sorry if it's been too quick, but I've just given you an overview of the Hartree-Fock approximation, the ideas behind the uniform electron gas, and then how that maybe fits into the slightly bigger picture. So that's really kind of, that's my overview. Does anybody have any questions on what we've talked about so far? Feel free to type in chat or stick a hand up or just unmute and shout at me. So Neve has asked, is it P that's equal to h bar times the wave vector? Yes, so that P is the momentum, and the momentum P is equal to h bar k, yes. So if you like to make a connection to classical formulas, then you can say that the kinetic energy of a classical particle is a half mv squared, which is P squared, where P is the momentum, over 2m. And then if you say P is equal to h bar k, you get h bar squared k squared over 2m. And that makes a kind of a nice little connection between classical momentum and quantum mechanical momentum. Any other questions? Anything that isn't clear, anything you want to go through? How do you get the wave function for n particles from a Hartree idea? So basically, the way that you do that is you use a Slater determinant. So I'll just give you a very, very brief sketch of how this works. Excuse me. So a Slater determinant, if you have n single particle states, let me just find the right bit of my notes because I want to make sure I get the right bits in the right places. I have got this into hand, so I'll just make it up and make sure that I get it about right. So in general, a Slater determinant will be something as follows. So you approximate the wave function as being 1 over root n factorial, and then you have a big determinant, and you have phi 1 of r1, phi 1 of r2, phi 1 of r3, dot, 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 and then you have phi 2 of r1, phi 2 of r2, phi 2 of r3, dot, 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 phi3 of R1, and so on down there, and so on diagonally down. Okay, so that's a massive determinant, and you can play with that. And what it shows you is, so let's think about two particles. So just for two particles, what do you get? For two particles, you end up with the wave function is 1 over root 2, and then you have phi1 of R1, phi2 of R2, minus phi1 of R2, phi2 of R1. Okay. And if you swap two particles, then you'll find that that changes sign. Okay, so if you swap particle 1 and particle 2, then you get the same wave function, but with the sign flipped, and that's important for fermions. Gustavo's just asked, is that the same formula of the summation of the permutation operator? Yes, it's exactly the same thing. It's two different ways of writing the same thing. So essentially with the permutation operator, what you do is you start with phi1 of R1, phi2 of R2, phi3 of R3, phi4 of R4, and then the permutation will just swap electrons backwards and forwards until you've done all of that, and that builds up all of the sums. So with two electrons, you have two terms. With 3 electrons, you have a 3 by 3. Okay, and so you end up with you end up with 6 terms, and it carries on like that factorially. Any other questions? Okay, so Juan News asked a question saying, so n is 1 or larger always in the 1D box, okay? Yes, so the energy, the eigenvalues of the 1D system are very much determined by the length and by the number n. Those are the two things that determine the total energy. So this is an absolutely standard problem in quantum mechanics, is the 1D infinite well. So it's a little bit different to the periodic system, but it's very, very similar. And what you find is that you have the wave vector, which is 2 pi n over L, and then the energy is just h bar squared k squared over 2m. So you end up with the energy being determined by n squared in the 1D box, whether it's periodic or with hard walls. So yeah, the whole system is determined entirely by the length of the system and the number n of the wave vector. And the number n of the wave vector is what gives you the different eigenstates, different energy levels of the system. If you want to sort of know more, I can sort of suggest you a quantum mechanics textbook. So please drop me an email. My email is just david.bowler@UCL-AC-UK. If you don't have it, then bug Alex or Karen, and they can give you that. Okay. Has anyone else got any immediate or urgent questions? Because if not, then I will say that we'll finish the tutorial there for today. If you have any thoughts about what you'd like me to do next week, so again, next week, again, it's quite formal. It's a derivation of DFT. It's going through the whole idea of electron gases and how you get to DFT from a uniform electron gas. If there's something different that you'd like, something you'd find more helpful, please do let me know, either in advance or on the day. And you know, do please make sure you come along with questions. So unless there's any more questions, then I will end the meeting there.